Hi ho, my name is Max Joyce with Physics 2211. Today we're going to be talking about lab number 3, a black hole. Alright, so a quick overview. We're going to do an introduction. We're going to talk about a black hole. We're going to do a little bit of computational modeling, and then we're going to draw some conclusions. Alright, quick introduction. We're going to talk about gravity. We're going to talk about black hole. We're going to talk about circular motion. Remember the equation, they're going to be more important later. So gravity in a black hole, gravity is a non-constant force. Remember that equation. It's dependent on our r, that radius between the black hole and whatever our object that we're looking at is, right, our system, which is going to be that little tiny orange planet for this scenario, right? So at every single position on the orbit is going to have a different force of gravity. So that's what I mean by non-constant. Now, our black hole, right, it's going to cause strong gravitational forces on very large masses. You'll see it's going to be a huge mass. It's going to be something like e to the, times 10 to the 34th or something crazy like that. All right, and then remember, force of gravity between object A and B will be the same as the force of gravity between object B on A, just Newton's third law. All right, so talking a little bit about circular motion, I'm going to explain these two things with the picture on the right? So that purple line is going to be F net parallel. That, of course, is in the direction of, or in the direction of the motion of our object, right? Then perpendicular, of course, is going to be perpendicular to the motion of the object, which is that blue arrow. Now, the orange arrow is actually going to be our F net, just generally, as it's going through the center of what's holding us in, which is that gravitational force. Remember, these are not forces necessarily, these are just components, right? That's the main thing to remember. All right, so this is the computational model. Our goal, of course, was to find the black hole in part 1. So these initial conditions were pretty standard. We were given the star mass. Delta T is just essentially how many seconds are in one day. And then over here, this is essentially all the code we used. Sealing pass, kind of the first few, as there it's pretty standard. You're just finding momentum, change in velocity, change in momentum, final minus initial, that sort of thing. Then dp dt, of course, is just going to be the change in momentum divided by the change in time. That's what delta p and delta t is. Then F net is equal to dp dt. That's just Newton's second law. All right, now what's important is when we get down here and we're looking for F net parallel, right? So we know F net parallel is going to be equal to dp dt parallel. Now how do we find dp dt parallel? We're going to need to multiply p hat by the change in magnitude of the momentum divided by time. How we do that, that's just a standard abbreviation that we found in class, which is very simple. Now we just gotta use a little bit of coding language here. And yeah, so we know that our F net is going to equal F net parallel plus F net perpendicular, so we can change that to be dp dt is going to equal dp dt parallel plus dp dt perpendicular. So when we're finding dp dt perpendicular, we know it's going to be standard dp dt minus dp dt parallel. So essentially, as I just said, F net equals F net parallel plus F net perpendicular. That's what the last slide showed with the the thing, the little image we had. All right, so now we can just manipulate the gravity equation, which we found first. So that force of gravity is going to be equal to our g m1 m2 divided by r squared, and that's essentially what we do here at the bottom. And when we did that, we found out that the mass of the black hole was 1.16988 times 10 to the 34th power, right? So that's a massive essentially black hole. All right, so part 2, we're now in a spaceship, and we want to see the speed our spaceship, essentially the minimum speed our spaceship can go, such that we're not sucked into the black hole. So our velocity must be able to overcome the force of gravity due to the black hole on our spaceship. What I didn't add here was also we have a planet also, so it's important to note that we also need to find the strength of the force on the planet, and so we don't crash into the planet. Alright, so looking at the left side, this is just really standard code. We're just finding the force of gravity on the planet, which is just using the gravity equation and finding a bunch of unit vectors. So this is all like really standard, really simple stuff. The main thing I'm going to be looking at is the planet velocity and the ship velocity, because of course we don't want to run into the planet, and our ship velocity has to be pretty quick, right? So what we're doing here essentially is we're just applying the position update formula and the velocity update formula at every one of these time intervals. Still really standard stuff here. We're just really just using the notation in the code. So the main thing is that, right, is essentially how we get our speed. from there, we can just plug in different speeds, and we found out that the minimum around the minimum speed was a -2 times 10 to the +7th and 1 times 10 to the 6th. Now we got a negative speed in the x because, of course, we're moving away from the black hole in the x direction. If it was positive, we would just run straight into the black hole. All right, so finishing off with these questions, rate of change of momentum is different between net force because the rate of change is looking at like a specific time, right? So the rate of change of momentum at a specific time versus net force, which is of course like a total sum of net forces essentially, right? So part 2 with the what if question, instead of wanting to take a quick look and leave, you want to decide that you want to take an orbit. So essentially your initial velocity has to be exceptionally like fast, like you have to be moving much faster. Because essentially you're just going like in a circle, right? Your initial velocity is keeping you in, and you're just following the curve, right? So yeah, pretty standard stuff. All right, that's it.